A moment of a force is the tendency of that force to rotate the body it is acting on. So basically, if a force can cause a rotation, it creates a moment. Now, to keep things simple, let's say up front that a moment is the same thing as torque. And we learned about torque when we were learning about mechanical advantage. And you may recall the formula for torque is the force times its radial distance. Or the way we would write it is torque equals force times the radius, where this symbol right here is the symbol for torque. But if our moment is equal to torque, then we can say that our moment is equal to the force times its radial distance, or its radius. Or we could write it as moment equals force times distance, and you will commonly see it written this way. But the problem with writing it this way is this is also the formula for work. Work equals force times distance. And as we learned when we were learning about mechanical advantage, work does not necessarily equal torque. Therefore, it does not necessarily equal the moment. And so the way we would differentiate those two is we would say the work is equal to a force multiplied by the distance it travels parallel to the force applied, whereas the moment is equal to the force times its radial distance, or distance radius. And actually, real quick, let's take a moment to define what a radial distance is. And so a radial distance is the distance between a force and the center point that force is rotating around. And it's important to note that when you are dealing with moments, you should ignore any distance that is not perpendicular to that force. So let's talk about what we mean. Let's say we have some board that's nailed into a wall. And so we'll say that this is our board and this is a nail. And you might notice that if we apply some force to this board, it will behave sort of like a first-class lever. It would rotate around. So let's go ahead and call this force 1. And so what it would do is create some rotation around this nail or this center point, and that is what we call a moment. And so we'll go ahead and call this our moment, and we'll say that it's the moment that is, since it's going counterclockwise, we'll label it the counterclockwise moment. And we can actually say that this counterclockwise moment is equal to this first force multiplied by the distance this force is from that nail or that center point. And so we can go ahead and even label that for ourselves. We can say that this distance 1, this distance to our center point or our nail, is the distance, the radial distance that we would revolve around to create our moment. So our counterclockwise moment is equal to this force multiplied by this radial distance. And you'll notice that this force is going up and down, and this distance is going left and right, which is what we mean when we say perpendicular distance. Now let's compare that to some force over here off to the right side of this nail. Let's call this force 2. Well, this force would create a moment itself. It would cause this board to rotate around, and admittedly, it'd be a smaller radius. It's a smaller distance that this force would travel around this nail, but this nail would still be the center point, so it is also creating some moment, which we can call a moment clockwise, since it is creating this sort of clockwise direction. And so we can set this clockwise moment equal to our force 2 multiplied by the distance between our force and the center point, which would be this nail. So we could say this distance right here, which we'll label distance 2, between this pin or this nail to our force 2. And again, notice that this distance is perpendicular to our force. But this is what we're talking about when we're talking about radial distance. We are talking about a distance that represents some radius of a circle that would be created by a motion of a force if that force were to just go through. If you think about it, if we have a nail here and we push down on it, it would push on this board so that it would rotate around, or at least this force would rotate around in this circle. Now, you might be wondering how this pertains to engineering. What do these moments have to do with engineering? And the answer is structures. When an engineer is creating a structure, that structure should be in what we call rotational equilibrium. So let's take a moment to define rotational equilibrium. And all it means is all the moments in a system cancel out and add up to 0. And so what that would look like in math is we would say the sum of all moments equals 0. And so what does that mean? Well, let's say that these two forces cancel each other out. So force 2 would clearly have to be bigger than force 1. But if we got them to cancel out, we could say that these two moments are equal to each other, or the torques are equal to each other. So what we could say is that our counterclockwise moment plus our clockwise moment is equal to 0. All of our moments cancel out, they add up to 0. And so what do I mean? Well, what I mean is our counterclockwise moments is essentially equal to our clockwise moment. So any force causing rotation in this direction is canceled out by any force causing rotation in this direction. In other words, our moments cancel out, and there is no rotation, which again we call rotational equilibrium. And if you think about it, since these moments go in opposing directions, we can say that they are negative to each other. So we can even write that out for ourselves. We can say clockwise moments are negative to counterclockwise moments. And if you think about it, that makes sense. If they're going in opposing directions, one would be negative to the other in the same way that an upward force can be canceled out by a downward force, assuming that they're equal. But instead of up and down, these are rotating, and so we're looking at the rotational direction instead.